Hello everybody, I'm Giulio Tonellato and we talk today about control strategies for ground source heat pumps using standing column wells. One of the main problems to address when talking about global warming is the energy use, and in commercial buildings in Canada about 60% of energy used is used for space heating. To reduce it, the most conventional renovation solution is to substitute boilers with ground source heat pumps that use closed loop boreholes, but this costs many money just for the drilling. An alternative solution is to use standing column wells. This system draw groundwater directly from the ground and reinject it in the same boreholes and also in other boreholes, thus enhancing the heat transmission and requiring 5 times less boreholes than conventional systems. But there are still some obstacles to overcome: the lack of easy to use design tools and peak loads management. My work will focus on this last problem. The case study building is the École La Clé des Champs in Mirabel, Quebec. A 5 standing column wells heat pump system will replace a fuel oil boiler. The main features of standing column wells is that the groundwater availability is not anymore a problem because the groundwater is reinjected also in the same borehole, and is also possible to reinject part of it in another well called injection well. This increases the performance and is called bleed. But we must take care of the risk of groundwater freezing. A water heater is placed just before the heat exchanger as a safety measure, but its use should be avoided. You can see here the water heater in the image. My main research objective is to reduce electricity peaks, thus operating peak shaving. Here you can see in the image, for example, that you can pass from the red curve to the blue curve, operating peak shaving. But how you can do it? Anticipating the peaks by rising bleed to warm up the well, as already mentioned, by preheating the building, thus shifting the loads before the peaks, or by preheating the water storage tank, thus also operating load shifting. The benefits are to reduce pressure on the grid and reduce capital and operations costs. How to anticipate the peaks? This is achievable with predictive control. My work is divided in 2 parts. The first part is most focused on modeling. My approach to the model is to divide it in 3 parts. One is about the 3D energy modeling of the school that is made in Transys. Another model is the heating, ventilation and air conditioning system, always in Transys. And then the ground response modeling is modeled in MATLAB. MATLAB is co-simulated with Transys. The second part of my work is about controls. At first, I will use reactive controls to assess the performance of the system and to have a baseline. Afterwards, I will develop predictive controls. This kind of controls allows to optimize the system through weather forecasts. I still do not have complete results, so I can show you here only preliminary results. Here you can see the validation of the building energy model. I reconstructed the real energy use through energy bills of both the fuel oil and of the electricity boiler, and I compared it with my Transys prediction. Afterwards, I also simulated a conventional setback to see how the system responds. So you can see here the conventional setback passed from 19 degrees night setback to 21 degrees. This made just in less than 1 hour provoke a huge peak, a huge power peak, and most of it is auxiliary power, is the water heater. The focus of my work is to cancel or reduce this auxiliary power and possibly also the heat pump power. Thanks for the attention.